Hey there guys, how's it going? Mike coming back at you here with another video on Calculus 1. In the previous video, we saw several sample problems that required the use of the product rule and the quotient rule, and we also saw how we can come up with the derivatives of tan x, cotangent x, secant x, and cosecant x by using the quotient rule. Today we're going to get into compositions of functions, as well as how do we take the derivative of a composition of two functions via the chain rule. So first of all, just a quick little recap. If I take two functions, f of x and g of x, so one function f and another function g, I can take the composition of these two functions to get f circle g of x, or f of g of x. And f of g of x means that I'm going to take the entire function g of x, and I'm going to have that take the place of any variables in f of x. So the question is, how do we come up with the derivative of this composition of these two functions, f of x and g of x? Well, before we get to the statement of the chain rule, I just want to quickly go through a couple of practice problems of taking a composition and breaking it up into its components, because this is going to be a very handy skill for you to have down when working with the chain rule. The chain rule is a common formula that people tend to mess up, and if you don't correctly identify the pieces making up your composition, then the problem just falls apart. So I have my first example here. H of x is e raised to the power sine of x. Now, this is a composition of two functions. I can say that this thing right here is of the form f of g of x. So what I want to know is, what are these functions, f of x and g of x? What are these things that are making up my composition? F of x is the outside function. G of x is my inside function here. So just taking a look at e raised to the power sine of x, we have our basic kinds of functions here. We have sine of x, cosine, tangent, any basic trig function. We have our basic exponential function, our basic logarithmic functions, polynomials. So think along the lines of these nice basic functions. So what are the two basic functions making up my composition here? Well, it looks like we're taking the function sine of x and we're plugging it into the exponent of my e. So that thing that I'm plugging into the exponent, that is what's going to be my inside function here. So that sine of x is going to be my g of x in this case. So g of x is going to be the sine of x. My outside function, what is that sine of x being plugged into? Well, picture that sine of x, that function, that sine of x, just being replaced with the variable x. And that's going to leave me with my outside function, my f of x, being e to the x. You can go back and verify, and you can see that if you look at these pieces separate and then take the composition, I'm taking the sine of x, and I'm having that replace wherever my variable is inside of f of x. So that sine of x is taking the place of the x that is the exponent of my e, and we do indeed come up with h of x just like we had at the start. Moving on to the next example here, a little bit more complicated. H of x is equal to the fifth root of the natural log of x plus 8 to the power x. This one's a little bit more involved, a little bit more complicated, but we see that we have the sum of two basic kinds of functions. We have a straightforward logarithmic function and a straightforward exponential function, and we're raising that whole thing to some power. Thinking of it as some basic functions all being raised to some power, that's our first hint as far as what is my inside function and what is my outside function when working with this composition. So again, I can write this as the composition of two functions, f of g of x. The question is, what is my f of x and what is my g of x? Well, again, going back to the statement of what we have here being some stuff being raised to some power, all that stuff being raised to some power, that's the verbal to mathematical cue that all the stuff that's being raised to that power, all that stuff on the inside is my g of x. That's going to be my inside function. So g of x here is going to be the natural log of x plus 8 to the power x. And now, this inside stuff being raised to that power, we just need to think of what is the outside function. What is that thing that has a power? Well, again, picture your inside function now just being replaced by an x. So it's going to be the fifth root of x, or x raised to the 1/5 power. And you could, once again, take the composition f circle g, and you get ln x plus 8 to the x raised it to the power 1/5, or exactly what we have for h of x. The fifth root of the natural log of x plus 8 to the power x. So these are just a couple practice problems here just to get our minds back into the gear of working with compositions of functions here. If you can clearly identify what are the pieces making up your composition, then I can promise you right now that is going to make your life so much easier when it comes to finding the derivative of the composition of two functions. Now we'll move on to the actual statement of the chain rule. So if you have the composition of two functions, f of g of x, and you differentiate it, what do you get? Well, by the chain rule, the derivative of f of g of x is equal to f prime of g of x times g prime of x. So you're taking that inside function and you're plugging it into the derivative of the outside function, and it's that times the derivative of the inside function. Now, just the statement of the formula by itself can be kind of confusing. I know this is a very easy formula to get messed up. So what I'm going to offer in the next video is a nice broken down sort of step-by-step way which you can use to keep your pieces straight and then just substitute those pieces into this formula. So in the next video, we will be doing several sample problems as to how do we use the chain rule to come up with the derivative of compositions of functions. If you have a question or comment, leave it in the comment section below. Otherwise, until next time, so long.